which would be a pity. And let me start sharing my screen. Okay, good. Hopefully you see it now. Yes. Do you see my slides?
Yes.
Yeah, very good. Very good. Okay, so just if something is technically not working, please tell me it at once, because I don't have contact with you, don't see you, so it makes things a little bit irritating. Okay, so a tree is a tree. So it's a thing which looks like a tree. So in other words, it's a connected graph. We'll be talking now about non-directed for the time being, but then we'll extend it to directed as well. So it's a connected graph having no cycles. So it looks, I don't know if I can try to draw. Well, there will be examples quite soon. Yeah. So things like, okay. So in the forest, it's just a disjoint union of some number of trees, or you can say it's a loop-free graph without cycles. You don't require connectivity anymore. So here we have very simple examples. This is a tree on 4 vertices, 1, 2, 3, 4, and this is a forest consisting of 2 trees, one on 4 vertices, and this guy on how many? 6 vertices. Okay, so we'll be talking about given a graph, the important trees which it contains. So first of all,
a question. Just a question on this forest. Does it have a minimum number of components, like minimum 2 components to be a forest?
Yeah,
or can a tree be a forest?
It's the question of terminology. Sometimes you include trees into forest. I think it's natural to include trees as special cases of forests. I mean, if you look at this definition, a forest is a loop-free graph without cycles. So this in particular include trees. I think in many cases, it's natural to include trees as special type of forests. So forest is just a more general notion. Okay. So a certain type of a tree which will be useful for us in this lecture is the following object. Say if you have a bunch of sets, we'll be assuming that they are finite, A1, A2, and so on, AN. Think of them as just points with labels. Now, sorry, I'll be creating my vertex set in the following funny way. I'll be taking union for all k starting with 0 to n, and I'll be multiplying for a given k. I'll be multiplying a1, you know, the usual Cartesian product, Descartes product, a1 times a2 times a3 times ak to the kth thing. And now this would be my set of vertices. And now I'll be connecting. Which vertices I'll be connecting? I'll be connecting a vertex which correspond to a sequence lowercase 1, a1, lowercase a2, and so on, lowercase ak. So I'll be choosing some elements from the first k guys. 2. I'm picking the same guys as here and adding any element from the next set, capital AK plus 1. Okay, so maybe it looks a little bit abstract, but let me show how this works in practice. So here is what happens if we have 2 sets, A1 and A2. A1 consists of 3 elements, and A2 consists of 3 elements here. Maybe it was not such a good picture. Maybe it would be better to have A1 3 elements and A4 4 elements, just to not to get confused. Okay, but the thing is that we start with an empty product, which we mark by a star. This would be our special vertex. Now we put vertices of the set A1 here. So this is A1, it has 3 vertices, 1, 2, 3. Now we'll be looking at sequences A1, A2. So we have, let me maybe, yeah, let's see if I can do that. Okay, so if I have a pair A1, A2, so now I'm looking here, I'm connecting this guy, A1, A2 to A1. So if say A1, yeah, so how should I say? Maybe let me see if I can. Okay, say A1 is, I don't know, yellow, green, red, and A2 is 1, 2, 3, 4. So we'll have vertices, for example. So these vertices would be just yellow, green, red. And these vertices here would be of the form, say, yellow and 1, then yellow and 2, yellow and 3, yellow and 4. Then we'll have green and 1, green and 2, and so on. And I'll be connecting, for example, this guy, yellow and 3, this would be this vertex here. If this is yellow, this is just the vertex yellow, and this is vertex yellow and 3, it should be connected to yellow, and only to yellow. Okay, so in this way, we will be getting a tree. So there will be no cycles. So each vertex, so we have this vertex corresponding to the empty set. Now each vertex corresponding to a sequence A1, A2, and so on, AK is just connected to a unique vertex which we obtain by crossing away the last element here. Okay, let's see. I hope that's somewhat clear. Why? We'll use this a little bit later. Okay, now important thing for a given graph is the notion of its so-called spanning tree. Again, we assume for a second that our graphs are non-directed and probably contain no loops. So it's a spanning tree if it's a tree containing all vertices of the original graph. Okay, now we have the following fairly simple remark that if a graph admits a spanning tree, then it has to be connected, of course, because if a graph is not connected, there is no way we can find a tree which contains all its vertices, because the tree is a connected subgraph, and if our original graph is not connected, so we have no chance. Okay, now the next proposition again is fairly simple, is that any connected graph contains at least one spanning tree. And how to do this? Well, I looked at this proof yesterday. It was easy. So we'll give a proof for finite graphs. It even works for infinite graphs, but we don't quite care about those. Well, so how can you get a spanning tree if you have a connected graph? Well, you can argue in the following simple way. So assume that if your original graph is a tree, there is nothing to talk about. So then it's its own spanning tree. Well, if it contains, yeah. Let's see, how was it? Okay, so here it suggests look at all possible subtrees, not necessarily maximal, not necessarily spanning trees. So, for example, a tree can be just one single edge. Why not? So this set of possible subtrees is not empty. Now, we're saying that but it's also, if our original graph is finite, then this set is also finite. And we say that it contains a maximal element. Well, a maximal element meaning that it's maximal by inclusion. So we cannot add any edge to it, so it still would be a tree. And the statement is that such an element must be necessarily a spanning tree. It has to contain all vertices. Once again, a tree such that whatever edge we're adding to it, it will not be a tree anymore. It has to be a spanning tree. Okay, why not? Assume that we have, so we have a vertex which we haven't included. Yes. Okay, if we haven't included a vertex, then okay, so we can definitely so there is a path from this vertex connecting it to, since our graph is connected, so it says here, so choose some vertex among vertices of our tree, and the path from this vertex which is not in our set to a vertex W which belongs to our tree, and such a path obviously exists since this is connected. Okay. Let's see. So this path, so it's fairly simple thing. Let's see. So maybe I can do a drawing instead on my iPad. Okay, so say we have a tree and it's maximal in terms that whatever edge we are choosing, additional edge, we are not getting a tree anymore. And we assume that we have and we are sitting in a connected graph G. So we are saying that if we have a vertex here, which is not in our tree, then something is wrong. Okay, so let us connect V to some vertex in our tree. Okay. And let us by a path. Path meaning we do not use edges repeatedly. So it hits our tree sometimes first. Okay, so so if these are vertices on our tree, So this path which connects V to a vertex inside will first hit. So we're looking at this path V, say, so V1 is V, then V2, V3, and so on. So it goes to W, which is an element in our tree. So we're looking, is this vertex already in a tree? So we're looking at the first vertex, which would be a vertex of our tree. So we know that this last guy belongs to our tree, but maybe it hits our tree earlier. So say this would be the first vertex belonging to our tree. Then we're picking this initial segment V1, V2, V3, and we'll be adding it to our tree. So once again, I will repeat, here is our tree, and here is our additional vertex V, and we are finding some path. And here is the first time it hits our tree. Say these vertices are not in our tree yet, but that's the first time it hits our tree. We're taking this thing. This would be a path, and we'll be gluing it to our tree. And the claim is what we get after gluing this path to our tree would still be a tree and a bigger tree. And this is a contradiction with the maximality. Because the condition that the tree is maximal is that whatever edge we'll be adding to it will not be getting a tree. And why is the result of the gluing a tree? Well, we're not creating any cycles, so we can only create a cycle. So the graph we started it was a tree, so we cannot create a cycle if we'll be using all new vertices except for the one which is at the end of our path. Okay, I don't know whether it was so convincing, but that's at least what the argument is. Let me go back. So here is a simple example. Yes, so the recording continues. Yes, good. Okay, so if I have a complete graph, for example, so it's very easy to find a lot of different spanning trees here. The most trivial example is to choose one vertex in a complete graph and to connect it to all other vertices. You'll get a so-called bush. So it's just a central vertex, and then it connects to each other vertex by one single edge. Say if we have, and that's the only thing which exists for a graph K3. So there are three possible trees here, like this, okay, so well, you see, so like this, like that, and like that, and all of them have that form. But already if we start with the graph K4, which is shown here, it's still a planar graph, then we have more options here.
We don't see what you show us. We see your face right now.
Okay, I'm not sharing my screen now, yes? Oops, I'm sorry. Sorry, very good that you told me. Let me tell, yeah. Do you see it now, hopefully? Do you see it now?
Yes.
Okay, very good. Sorry, so if this is graph K4, and K4, for a K4, you can also do it like this. You can start with a vertex and connect it, say, to three other vertices, 1, 2, and 3. So you get a small bush. This is a central vertex, and there are three edges connecting it to the remaining three vertices. This is one type of trees, but there is also other type of trees here. For example, if you go like 1, 2, 3, you'll get a path of length with 3 edges. This is not a bush anymore. That's a different type of trees. And in this specific case, there are only 2 types, either a bush and or a path of length 3. But as soon as you go to K5 and K6, you see that the number of possible types of trees with a given number of vertices will increase quite quickly. And I think I did some small exercise for you earlier, but we can also repeat it now in very soon. So for example, for this graph, which we already used several times, the Pedersen graph, here is one example of a tree. So the trees, so what is the edges of a spanning tree are marked by stars. So what do we have here? So we start with, yeah, I guess, so we start with this edge. We start with this vertex, sorry. So we take 1, 2, 3, these 3 edges. Now we add this guy and these edges. Yes. We go here and we add those 2 edges. And now we cannot add anything else because then we'll be getting a cycle. So if you look at, if we take the edges which are marked by stars on these pictures and their vertices, of course, the endpoints, you'll be getting a tree here in this graph. And one thing which is not in your lectures here is this famous Kirchhoff theorem. Let me maybe make a small note here. Kirchhoff's theorem. It's very nice and important. The theorem. So the number of spanning trees equals the determinant, I'll move it, the determinant of the adjacency matrix, adjacency matrix. Determinant of the adjacency matrix very sorry, it's annoying. Adjacency matrix with, say, the first row and column removed. It's a very, so it's a very important result. And it's very interesting that this determinant does not depend, it's not about the first row and the first column. You can remove any column I and the correspondent row I. You keep the matrix symmetric, so you remember that probably that the adjacency matrix is a symmetric matrix where the rows and columns are labeled by vertices, and there is a 1 in the position if the ith in position ij, if the ith vertex is connected to the jth vertex, is a nice symmetric matrix with real spectrum. Now, if you take it and remove some column number I and some column and some row number I, you'll get again a symmetric matrix. And it turns out that its determinant independently on for which I you do this will be the same and will be a positive number equal to the number of spanning trees. Very nice, important result. Okay, so so let us go further to a very simple, again, characterization of a tree. So what is a tree? So a tree can be characterized in two different ways, which are most usual, but then there are many other characterizations. But we'll be talking, what is a tree special? It's a connected graph with special property. One of the special property is that for any two edges, for any two vertices in a tree, there is just it's a connected graph, should be a path connecting them, and this path is unique. Since there are no cycles, you can only choose one single path connecting any two vertices. There is no ambiguity in this choice. Another simple thing is if we'll be talking about finite graphs. So a tree is a connected graph where the number of edges equals the number of vertices minus 1. So in a tree, if you try to draw it, you'll immediately observe that the number of edges equals the number of vertices minus 1. Okay, so why is this true? Let's see. Okay, so just 1 second. So say 1 implies 2. Given a tree, each two vertices can be only connected by a unique path. Well, assume that we have a cycle. So a tree is a graph with no cycles, connected graph with no cycles. So assume that we have a cycle, then in a cycle, say this is something like a cycle. In a cycle, you can connect any two vertices lying on a cycle by at least two different paths. So we know that a path, since our tree is connected and a path exists, and assume, and it should be unique because as soon as we have a cycle, we'll get several different paths. Okay, now why is it that if we have a tree, then the number of edges would be by 1 less than the number of vertices? Okay, what is it that we want to say? Yeah, we want to say that if we have a tree, then either it's a trivial thing consisting of just one vertex, or it should have a so-called terminal vertex in the, I think, a terminal, also called a leaf. A vertex with whose degree is 1. It's just something yes, it's just yes, hanging vertex, I guess. Okay. And why this should be true? Okay, so why should a tree contain at least one hanging vertex? Let's see. assume that there are no vertices of degree 1. What happens then? Okay. So let us look at the path of the maximal length in our tree. Okay, then if so we'll be looking at the path of maximal length, and then if this is not a vertex of valence of degree 1, then it is connected to some w, which is not the previous thing in your path. And then you can extend. Then you can either extend your path, which contradicts to its maximality, or you will be getting a cycle. Okay, maybe I should try to explain this by drawing. Sorry, let me do that. I have to jump back and forth a little bit. Okay. Okay, so the claim which we have is every tree contains a leaf. And the leaf is a vertex like this. This is a leaf. So, which is a vertex of degree 1. Or hanging vertex, sometimes it's called. And why? Okay, and the argument is as follows. So assume we're looking at the maximal path. Take a maximal path. A maximal means that we cannot extend it anymore, not creating a cycle, and not, we cannot extend it. Take a maximal path, and now look at this guy, Vn. So since its degree is bigger than 2, it's not a hanging leaf. We are assuming that there are no possible hanging leaves. Then it is connected to some W here. And this W is different from this previous vertex here. So then if it's because the degree here is bigger than 1. So, and then we are in two situations. If case 1, if W is not in a path, then the path is not maximal. Or case 2, W is in a path, but then we're getting a cycle. Then we have a cycle. Okay, so that means that we should have at least one leaf in a tree. And then we want to show that from having a tree, so lemma is for a tree, call it T, we have that the number of vertices equals the number of edges plus 1. Okay, and how the proof goes, so we have shown that a tree, so we'll show by induction on the number of vertices. Induction on the number of vertices. Okay, so for for a tree with 2 vertices, so we just have 1 tree, is true. So this is induction base. Now induction step would be, so given some tree, given a tree on n+1 vertices, find its hanging vertex, its leaf. So say we have found some leaf, A, and cut it out with its edge. Okay, so we'll be removing this piece. A is not connected to our tree by anything else because its degree is just 1. So the remaining thing, the remaining graph is a tree on n-1 vertices. Why is it 3? Why it should be connected? Well, it's connected because if we look, so this original thing was connected. Now it means that it has a unique path between any its 2 vertices. And if we're removing the hanging vertex, the leaf A and its edge, so it can only involve paths, the paths going to the leaf, because no other paths between all other vertices can never use this unique edge connecting A to the remaining thing. So the remaining thing the remaining graph will have exactly the same property. It will be connected, and there will be unique path connecting any 2 vertices in it. So that's why it's a tree. And for a tree, oh, okay. So sorry, this was n vertices, not n+1. So we have on n vertices for such a graph by induction. So we have that we have our statement that V of this tree, which we obtain T prime. So this remaining thing would be T prime after we remove this thing. It will be the number of vertices equals the number of edges and T prime plus 1. And then we'll be just adding 1 edge and 1 vertex. So plus 1 here, plus 1 here. And we'll be getting, so V of T equals E of T plus 1 for our tree on n+1 vertices. So that's how the argument goes. It's really quite simple. Let me go back to my screen here. Okay. Let's see. Yeah, maybe it's time to make a break now. Yeah. So we'll continue in 5 to 10 minutes. Good. Yeah. So stop share and pause. Okay, so I'm back. Let me do some small exercises before I continue.
Jag hittar ingen app för det. Du måste ladda ner den. Du kan prova.
Do some small exercises. Okay, good. So first of all, I want to explain another way to think about why each connected graph contains a spanning tree. So what we should do, we should remove, if I have a graph with a cycle, we should just take any edge in this cycle and just remove it. And in this situation, the remaining graph will be still connected, and we can continue doing this as long as there are still cycles in our graph. And once we destroyed all cycles, we'll be getting a tree. Okay, let's do some example. Removing edges from a graph to get a tree, to get a spanning tree. Okay, say we have a 5 gone, and we have maybe some more edges like this. So this is not a tree. It doesn't look like a tree, of course. Maybe I'll throw in one more edge here. Okay. Now, I'm saying that I want to get a spanning tree, just one from it. So what should I do? I should, if I find a cycle here, for example, I'm taking this cycle, and I'm saying I will remove any of its edges. Okay, here I'll be removing this guy, for example. What I'll be getting graph like this. It's still connected because any vertices, I'm removing one edge in a cycle. I can still connect. If I have a cycle and I'm removing one edge, the remaining vertices are still connected by a single path. So that means that doing this, I'm not destroying the property of being connected. Okay, I'm looking again, I'm repeating this process. For example, if I'll be taking a cycle like this, yeah, you see this cycle. I'm saying I can kill any edge in this cycle, say this guy. Okay, so I'll be getting a situation like this. Yes. It's still connected. It still has cycles, yes. So we still have 2 cycles. So I can take maybe this triangle and kill, say, that edge. What is it we'll be getting then? We'll be getting a situation like this. And finally here we just have one cycle left, which is this triangle here. And say I'll be killing any edge in this. And what is left will be just a path containing all vertices. So by doing this, we can obtain, in fact, all possible spanning trees in our graph. So the idea is just if you have a connected graph with some cycles, you take any of that and remove one edge in the cycle at a time, and then repeat this procedure as soon as your cycles exist. Okay, yeah. Maybe as another small exercise, let us try to list how many spanning trees we have in a graph, say with 4, in a complete graph with 4 vertices, maybe. Yes. So if we think about possible types of trees, so trees with 4 vertices. So how many different types are there? So we can have a path, and there is just one other type, which is a bush like this. So in this case, there are no other guys. And say if we have labeled vertices A, B, C, D, then we can have, so these type of graphs, we're just choosing one of the edges, one of the vertices, sorry, and connecting it to all other vertices to get the bush. So there, in K4, there are 4 spanning trees like this guy, Now, how many, so this is a path. How can we get a path from K4? 1, 2, 3. So we have to just write down the sequence of any sequence of any so we have to put labels here since it's a complete graph. If we put labels A, B, C, D in some order, then we will be uniquely choosing a path. So the conclusion is in K4 there are 4 factorial, which is 24 spanning trees like one long path like this, because and they're in one-to-one correspondence with putting our labels of our vertices A, B, C, D, A, C, D, B, and so on. So there are 24 permutations on 4 letters, and each of them will code a unique path, since we're working with K4 and the unique spanning tree. Okay, let me go back to our new material. Just 1 second, I'll close the door and continue. So we'll be talking now about rooted trees. Just 1 second. So a rooted tree, as it says in this definition, is just a tree where we choose one vertex and say this is our root. That's the vertex we'll plant into the ground. So, for example, in this case, which we discussed in the beginning, we had, maybe I'll go back to this example just to show it once again here. So we have a natural root which corresponds to taking an empty set, an empty product of our finite set. So this guy was a root. So we plant it into the ground, and these would be branches growing from our root, and this will be further branches, and so on and so on. Okay, so mathematically we're just choosing one single vertex and saying that this would be our root. Okay, so a directed graph, a directed tree is just a tree. A directed graph whose underlying graph is a tree. So now if we have a rooted tree, so we have been chosen one vertex and saying this is our root. So there is a unique natural orientation such that, so the root would be placed into the ground, and then there will be unique orientation such that for all vertices except for the root, we'll be having incoming degrees equal to 0 and outcoming degrees. Okay, and for the root, the incoming degree would be 1. And again, it's very simple to explain what is going on. Let me do it on the picture again. Yeah, sorry, I'm clicking back and forth today a lot. Okay, so standard orientation of a rooted tree of edges of a rooted tree. Okay, so we have some tree. And say this is the vertex which we call our root. So our tree is connected. So we'll be looking at vertices immediately connected to the root. Say in my picture, it's just one. It could be, in fact, more. Let me do some more like this. So I'll be orienting the edges which are connecting my root to its immediate neighbors upwards. Now I'm taking my new vertices which I obtain on this step and looking at their immediate neighbors which are not the root. Yeah, so here we have two. And again, we'll be orienting them from the vertex which we are sitting at to our new vertices like this. Oops. And for this guy, we have two more and we'll be orienting them like this. Now, again, we obtain a bunch of new vertices. If these vertices are terminal vertices or leaves, so they will stop considering them. If one of our new vertices is not a leaf still, then we'll be looking at its neighbors, which we have not been considered yet. So for this guy, we'll have three more, this, that, and that. And we'll be orienting from the vertex we seated to our new vertices like this. And again, we'll be looking at the new obtained vertices. If some of them are leaves, we'll just stop thinking about them. And if some of them are not, like this guy, we'll be looking at the new vertices adjacent to this to this thing. And again, this will be unique way to orient it, unique way to orient it, unique way to orient it. So I hope you understand what we're doing. So, and again, the in degree, the number of incoming edges to each vertex except for the root would be exactly 1. And for the root, it would be 0. Root is our initial point, and from the root, we'll be propagating along the tree, orienting each time towards new vertices. Okay, good. Yeah, here is an illustration again in this case, which we considered when we are getting the Cartesian product of a finite number of sets and creating vertices as lists of elements from our sets. First, the empty guy, which correspond to our root. Then those which correspond to elements of A1. Then there's those which correspond to pairs of elements A1, A2. This would be on this level. And then A1, A2, A3, the next level, and so on. And the rotation would be downwards on this picture. From the root to elements, to one element, to one entry elements, two entry elements, and so on and so on. Okay. So if we have a rooted tree, we can associate to each vertex its level or its length, maybe, I don't know, level of a vertex. Here it is. It's what is the distance of this vertex to the root. We know that each vertex is a tree is connected to each other vertex by a unique path. So we'll be measuring the distance to the root. For each vertex, we'll be counting how many edges we need to have to connect our vertex V to the root. Okay. so yeah. So a child of, okay, so we'll be stratifying our vertices by different levels. So our, say, the root would be level 0. Its children, its vertices to which it's immediately connected would be level 1. Then the children of the children would be level 2, and so on and so on. Okay. Now, the last thing maybe I want to do, is it the last thing for today? Yeah, it seems like this. We'll be introducing, for a rooted tree, we can introduce a lexicographical order on its vertices. And let me show you again how to do this on a picture. And maybe we can do some small exercises afterwards before we part. Okay, so lexicographic ordering of vertices on a rooted tree. And that's the way to do this, is as follows. Yeah. Good. So lexicographic order of vertices of a rooted tree. So once again, if we have a rooted tree, so say this guy is a root. Now we have vertices of level 1. Now to vertices of level 1, we have some vertices of level 2. For example, like this. Now to these guys we have, I don't know, some level 3. So maybe some guys die here. There will be no further children. Some guys still continue. And do like this. And we does have to we don't require that we go to the same bottom level. So level 5 and level 6. And I want to associate it to associate to my vertices a certain partial order. So I want to say no, it would be a complete order. So we'll say which vertex is smaller than which. Okay. This would not be, the lexicographic order is not uniquely defined, but it's you can, there is some degree of freedom on this, you'll see. Okay. So to define a lexicographic order, one has to order all children of any given vertex. Okay, so let me explain what I mean by that. Say I'm saying that my root, so my root is the biggest guy. My root is the biggest vertex. So I start with this. Now I'm looking at its children, for example, and well, in my picture, well, my plane drawing is in fact is already lexicographic ordering, because if I'm doing if I'm saying that I'm looking at the children of the root and say I'm ordering them, I'm depicting them on the plane and say I'm ordering them from left to right. So say order. So this is step 1, step 2. Order its children. So for example, we're saying this guy is smaller than this, smaller than this, smaller than this. Okay. Now for each vertex of this level, again, so I have ordered my vertices so far, level 0, level 1. Now I'm looking at the children of the children. I'm looking at vertices of level 2. And what I have to do, I have for one given parent, I have to order its children. Say I'm ordering these two guys. This is smaller than this. And these 3, so this is, again, so this would be the increasing order, the increasing order, the increasing order. And
the size that you're ordering upon, is that all children all the way down, or just the direct children you're basing the order on?
no, so I mean, this arrow is, I'm just ordering, I have to order these 3 children of one and the same father so far. And I'm saying this child is the youngest, this is older, this is older. And I'm doing this for each specific father. Okay. So when I have done this, when I have ordered the children of each father, then I will define my global order on all vertices on the tree as follows. So so then each vertex, so after doing this, after doing all this local all local orderings, I have the following. So each vertex has a unique path, connecting it with the root. Yes, with the root. Say I have I don't know. So I start with my vertex, so V, and then I'm say V is V1, then we have V2, V3, and so on, V3, and finally I'm ending up with a root. And I have, say, W is W1, W2, W3, and it connecting it to the root. The path doesn't have to be of the same length. Okay, and maybe I should write it the other way around, starting with the root, but don't bother. So and so if I want to say that, we say that V is smaller than W if the first distinct element in the path connecting the first distinct element from the bottom in the path connecting V to R is smaller than that for W. Okay, so what do I mean? So we know they all go to the root. So they end up with the same element R. So we have to look at the previous element here. So I don't know, V, maybe K, and here we have WL. So these two guys, VK and WL, they should be sons of R. Yes, so it should be immediate. They should be on level 1. They should be here because after on the next step we're connected to the root. So we have I don't know, V. What was the indexing there? VK and WL. So we have VK here and WL here. So if WL is bigger than VK, then we're saying W is bigger. The whole W is bigger. If they are the same element, say assume that they are the same, for example, then we have to move further. So if VK is smaller than WL, then V is smaller than W. The other option is if WK equals WL, then go further, go to the next elements. So if these guys, if we have R here, some element, I don't know, U here, and the same guy U, so that means that the end of our path connecting, so we'll be doing something like this. This is R, this is U, and then our paths will probably split again. So we'll be comparing these two guys. This would be lie on level 2. If well, either they coincide or one of them is bigger than the other, because we have chosen an ordering for all children of one and the same vertex. So either we know which of them is bigger, and then the correspondent original vertices V would be smaller than the correspondent vertex of W, or they're again the same. If they are the same, so our paths connecting V and W to the root have two equal vertices, 2 equal edges at the end. But since these are distinct vertices, at some point they should split. And when they split for the first time, we have to look which of those guys were bigger than the other one. And we'll say if this is smaller, then this vertex is smaller, and this vertex is bigger. So since V is a different vertex than W, at some point the path connecting V to R and W to R should split. And that's the essential point. We are looking at the moment when they split, which of the immediate children were bigger than the other one. And this define which V or W is bigger than the other one. Okay, so I think I'm done with the theory. Maybe let's now do some small exercise. Count the number of non-isomorphic trees, say with 7 vertices. Let's just to experiment, do some exercises. So we want to have 7 vertices, and the simplest type of tree with 7 vertices is of course just one long path. Yes, 1, 2, 3, 4, 5, 6, 7. That's one tree. So what can happen otherwise? Okay, so let me see if I can draw all of them. We can get, so here we have all vertices of degrees either 1 or 2. That's in our first case. And as soon as vertices of degree 3 will appear, so okay, so we'll be getting a thing like this. Can we get another one? So we can also have a a situation like this, just one vertex of degree 3. It can be either in this position or in that position. And these are the only possibilities, because if we move it further to here, this would be isomorphic to itself. So the vertex of degree 3 is either the immediately close to the leaves, to two leaves, or it just close to one leaf, and then it should be in this position. Okay, say we have two vertices of degree 3 in this situation. Can this happen? Yes, it can happen, and we can have again two vertices of degree 3. We can have a situation like this. This is one guy, and this is another guy. Yes, 1, 2, 3, 4, 5, 6, 7. This is one possibility, and another possibility would be like this. So we have two vertices of degree 3, and the rest is uniquely defined, and I think this is it. There is no other. Let's see. Yes, so there is no other way to do this. So we cannot have three vertices of degree 3. This is impossible. But we can have a vertex of degree 4. So of degree 4 now, let's see, 1, 2, 3, 1, 2, 3. So this is 1, 2, 3, 4, 5, 6. Okay, let's see, like this. This is one option. What can we have something else? Yes, we can have a situation like this. A vertex of degree 4 and the vertex of degree 3. So for vertices of degree 4, yeah, by the way, we can also have a thing like this, I guess. Yes. That's another possibility with the degree 4 and then no degree 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. No, sorry. So this guy was wrong. So let me remove it. So there is no thing like this. Okay. Let's see. So here, can we have something of degree 4 and of degree 3? Yes, this is still possible. Say 1, 2, 3, 4. And the thing like this. Yes. This is a degree 4 and a degree 3. And this is the only option. And if we have a degree 5, finally, if we have a degree 5, 1, 2, 3, 4, 5, then we have 6 vertices already involved. And we can just glue one additional guy here. And this is all what it has, what it can be with a degree 6. I can show. So maximal degree is 2. Here, maximal degree in these two cases. So we have a degree 3, unique vertex with degree 3. Here we have two vertices of degree 3, and the rest is smaller. And here also, these two guys. Here we have degree 4, unique degree 4. And here beneath degree 4, here we have degree 4 and 3. Here we have degree 5. This is the only guy like this. And finally, we have the unique one, a bush with degree 6. 1, 2, 3, 4, 5, 6. Degree 6. Okay, so so try maybe at home if you have time, try to list all trees, non-isomorphic, with 8 vertices. And maybe try to count spanning trees in K5. So for this, you need to know how many non-isomorphic trees there are on 5 vertices. And this is not, let us do this, non-isomorphic trees with 5 vertices. And there are not too many because this would be what will be coming in when you work with K5, if you have time. So we have a guy like this, a bush, degree 4. Now, if we have a vertex of degree 3, so that it involves 4 vertices already. Let's see. Yeah, and then you have to add 1 leg to here. So that's the only possibility of having a vertex of degree 3. And finally, we have a path with 5 vertices. These are 3 possible types of trees. All of them will appear as spanning trees in K5, and you have to count how many times each of these will appear for different choices of labels of vertices. Okay, so let me stop here, and I'll do the usual thing. I'll put this on the web soon, and I hope you had some information. Okay. Bye-bye.